Hello and welcome to the first of these online presentations as we try and flip our classroom at ISA IB Chemistry. So I'm going to take you through some of the key points that you need to know for each section of the syllabus. We're going to start today with 2.1, the nuclear atom. First slide will always show you kind of an overarching understanding, and then the next slide will show you what you should be able to do by the time you've finished watching this movie. Now the beautiful thing about this is hopefully you'll be able to go backwards and forwards and revisit some of the trickier bits that you'll maybe struggling with. So this is what you should be able to do. Describe what atoms consist of, state where electrons are found in an atom, and explain how the relative atomic mass can be calculated. Some of you maybe already know how to do these things, but there's no harm in reviewing it. So, still getting used to this bamboo pen thing. A little bit of history, won't be in your exams, but maybe worth having a look at. Greeks had a first go at this many years ago. And you can see that we've got this idea of matter not being able to be divided up indefinitely. Aristotle working on this premise: earth, fire, water and air, there's 4 elements. Sadly he turned out to be wrong, but his theory did stick around for a long period of time. It wasn't until relatively recently that John Dalton came up with the first modern atomic model. These were some of his ideas. So atoms of an element are identical, all matter is made up of atoms. Atoms can be rearranged in reactions, and this formed the starting point for many other subsequent discoveries. So discoveries on the back of that: Dalton's billiard ball model, Thomson's plum pudding model, and then the Rutherford model, which is getting closer to where we are today. And you can see there the more recent one, Rutherford, showing that atoms are mostly empty space, and we've got these negative electrons orbiting a positive nucleus, and that's kind of the picture that we have today. So how were these theories put into place? Well, Ernest Rutherford did a lot of work with gold foil. He was firing alpha particles into these sheets of gold foil, and he was finding that most of them just went through, indicating to him that there was a lot of empty space in here. He did find though that some of them were either deflected or bounced back, and that said to him that there was a nucleus in amongst there. Later on, we've got some research happening that tells us that the electrons are in shells. We're going to come back to this in the next presentation, where we can look at electrons moving between these orbitals and evidence coming for that in these emission spectra, clear lines from these emission spectra. But we'll talk more about that in 2.2. Last piece of the puzzle: it had been proposed that there was another subatomic particle. In 1932, Chadwick did an experiment where he bombarded beryllium with some helium nuclei, and he was able to produce a new substance, and this neutron would knock something out. So something was forced out of the atom, and this has been very important in terms of nuclear physics. You think of nuclear reactors, if you're studying physics, you may be familiar with some of these ideas. Okay, so moving on to what we kind of really need to know for our exams. This, if you think of some of the theories that we've just seen, this is our model of an atom. We've got our nucleus in here, consisting of protons and neutrons, positively charged protons, neutral neutrons, and around that, mostly space, but you can see we've got these shells, as they're depicted here, of orbiting electrons. Now, in terms of their relative charges, we said that protons were positive, neutrons neutral, electrons -1. Relative masses, well, these have a relative mass of 1, neutrons have a relative mass of 1. Electrons, we can quote it as that, or we can also just describe it as being negligible. Right? So when we're considering the mass of an atom, we count the electrons as not really weighing anything at all. How do we show this? How do we show the number of protons? How do we show the number of neutrons? How can we work out the number of electrons? Well, this is the system that we use, where we've got the symbol for the element, we've got the proton number or atomic number here, and really it's the number of protons that defines which element it is. So for example, if something has 3 protons, it's a lithium atom. If something has 19 protons, it's a potassium atom. Now the top number, the mass number, everything that weighs something, so the total number of protons and neutrons. So we look down here at an example of how to work out some of these figures. Lithium, proton number 3, it means it's got 3 protons. It's neutral, okay, it's overall. So if we've got 3 positive protons, then we must also have 3 negative electrons. Right? So overall it's neutral, 3 positives, 3 negatives. And looking at how do we work out the number of neutrons, well, this 7 is, as it says here, protons plus neutrons. So if I've got 3 protons, 7 minus 3 means I must have 4 neutrons. Looking at potassium, how many protons? Well, 19 protons. How many electrons? Again, neutral, so it must be 19 as well. And then how many neutrons? 39 minus 19 is going to be 20. Protons in the oxide ion, notice this time it's got a 2 minus charge. How many protons are in there? Well, again, it's oxygen, so it's always going to have 8 protons. How many electrons this time? Well, if it was neutral, it would be 8. But this 2 minus means we've got 2 extra negative electrons. So it's 8 plus 2, which makes 10. Number of neutrons, different, 16 minus 8. 8. Aluminium 3 plus ion. So, aluminium, 13 protons always. How many electrons this time? Well, if it was neutral, it would have 13 electrons, but we've got 3 extra positives. So, it means we've only got 10 electrons in there. And how many neutrons? 27 minus 13, it's going to be 14. Like that. Last one, slightly odd one. The proton. Hydrogen, 1 plus ion. We'll see why it's called a proton in a moment, because it consists of 1 proton and nothing else. So particularly when you do acid chemistry, you'll come across this a lot more, and you'll see it's a very important entity. You'll refer to it as a proton because it is a proton. Okay, something else we need to cover, this term isotopes. So what are isotopes? Well, isotopes are entities with the same atomic number, so they have the same number of protons, but they have different mass numbers, so they contain different numbers of neutrons. And here's some examples. You've got hydrogen, deuterium, tritium, so 3 isotopes of hydrogen there. You've got 2 isotopes of carbon listed here, 12 and 13, so this one would have 6 neutrons, this one has 7 neutrons. And 2 isotopes of cobalt listed here as well. Where are these useful? Well, they are very useful compounds, and you can read around this if you're interested, but hopefully you're maybe familiar with carbon dating from isotopes here. Medical tracers, often used in the body to look for problems with blood flow, accumulation in various places in the body, and also something like this would be used in radiotherapy. Substances like cobalt-60 are emitting a lot of gamma radiation, and that can be used to kill cancer cells. Right, so we can examine these isotopes, we can look at these things with different masses in a device called the mass spectrometer. Now we don't need to know too much about its workings, but I thought it was worth having a look at it anyway. So our sample comes in the gas phase, and first step that it goes through is ionization. So we've got our gas particles coming in, ionization, and what we've got here is some really high energy electrons being thrown at it, and it's knocking electrons off our atoms. And so we end up with something that has a positive charge. It then gets accelerated through these charge plates and into this part of the machine, which is probably the most important section, because this is what separates up the isotopes that are coming through, and it's a giant electromagnet. So this is our deflection section. Now if something is very heavy, it's going to be less likely to change direction, and as a result it's going to keep going on its course. If something's very light, it's going to be able to change course very easily, like that. If something is just right, we might find that it goes all the way down here into our detector and we get a reading. And what we can do is we can change the strength of this electromagnet so that everything gets a chance to come through and be detected. So things are going to be deflected according to their mass, but they're also going to be deflected according to their charge. Now for the most part, the charge is always going to be +1, right? We tend to lose just one electron and we end up with these positive, unipositive ions coming through. Sometimes, very rarely, we might find that 2 electrons are knocked off, and in that case our charge would be +2. And if something has a higher charge, it's going to be easier to deflect, so we'd see a slightly different reading for that one. Typically, generally speaking, we're only going to be dealing with these +1s. So essentially, things are getting separated by their mass. And this is the printout that we might get from a mass spectrometer. So someone's fired in a sample of zirconium into our device here. It's gone in, and maybe I should just point out, maybe I didn't mention it a moment ago, but we've got this vacuum pump here. Hopefully you can see that it needs to be a vacuum so that my particle can move freely through here. I'm not going to be detecting oxygens or nitrogens or anything else that's in the air. So we have it attached to a vacuum. But once we've run it, we're going to get a reading like this. So these are different isotopes of zirconium. Some have a mass of 90, some have a mass of 91, 92, 94 and 96. And you can see here that the x-axis is referred to as the mass to charge ratio. And so normally, as I said, the charge is going to be +1, so we're kind of separating things by their mass. So this has a mass of 90, mass of 91, mass of 92. If we're in a very unusual situation where our charge was +2, we'd be dealing with numbers around about 45. Right? You can see that would be half of that number. The y-axis is the relative abundance, and that tells us how much of each of these isotopes we have. Now we can take this information and we can work out the relative atomic mass of an element. And so this is the number that you'll see quoted in your IB periodic table in your data booklet. It's got a couple of decimal places after it, and it's worked out using a mass spectrum. It's an average of all the isotopes that are there. So to work it out, we need to do a kind of weighted average calculation. So if we were to find out these heights, and you could read them off the scale, or you could measure them with a ruler, you would end up with this data. So here's our data, and we can process that data. If we look at our relative percentage abundance, we can like to do a weighted average data we've got. So we've got 51.5 times 90 plus 11.2 times 91 plus 17.1 times 92 plus 17.4 times 94 plus 2.8 times 96, and that's going to be parts of the total. The total is 100. That's the sum of these, and if I work that out, my answer comes out to be 91.318. And as a check, you can see it's sitting somewhere in these figures. Right? If I was getting a number that was like 200, I should be able to see that I've done something wrong. Now usually, this number here will be 100. Right? But we might find instances where if we've measured the lines ourselves, for example, and we've got different values in millimeters, it's not going to be a percentage part of 100. So in that instance, we just do what we've done here, just add up whatever you've been multiplying through by and get your reading like that to be 100. So I put this one in just as a little bit extra. It's actually a molecule, chlorine, Cl2, and if we were to run that in a mass spectrum, we would find the following pattern. And we can have a look at where that pattern's coming from, and we could maybe think of it in terms of, well, why, if I look at my periodic table, does chlorine have a mass of 35.5? Well, chlorine exists in these two isotopes, 35 and 37. And just looking at these to answer that 35.5 question, if I was to measure these, my chlorine 35 maybe has a height of about 15, and my chlorine 37 maybe has a mass of about 5. So if I do the same calculations we just saw in the last slide, be 35 times 15 plus 37 times 5 over the total. Remember I said it didn't have to be 100, the total here is 15 and 5, which makes 20. And if I work out that sum, thanks to that weighting, it's 35 and a half, which is what we've got here. So now we can maybe use that idea that we've got these two isotopes to address well, what's happening up here. Well, if we're dealing with Cl2, if we combine two of the 35s in our molecule, then the mass of that is 70. This would be a 35 and a 37. This one would be two 37s. Like so. And you can see because we have relatively few of the 37s, we certainly don't have very many of these. Okay, so this is what you should be able to do, having watched all that. If you can't, please go back, revisit some of the sections. And you'll also see this tagged onto the last slide of the presentations. If you like learning stuff online, you might be interested in this ebook. There's a link here to